All right, let's get started. So a couple of announcements. So I'm still working on grading. I have a lot of students in my online Chem 104 class, so I was busy trying to grade all their stuff first before I tackled yours. So there I am with the grading. But kind of my thoughts, so I've only graded like the multiple choice questions so far, and they're perhaps not as high as I would like them to be. We'll see how the overall grades shake out. But I'm probably thinking that we'll do no quiz on Thursday, but instead maybe do some sort of test corrections or something. So look for that on the horizon. I don't have, again, like points or anything, but just kind of based off of what I'm seeing, I think it'd be good if we worked on some test corrections and went over some of those tricks of the testing, since I think just people panic on exams instead of just kind of focusing on like what the trick of the problem is. So we'll kind of do that. All right, and then we're starting chapter 17, so we'll probably also do the acid-base math, the titrations on Thursday as well, towards the end of class. So again, just hang on to those labs, and we'll do the pre-lab 7 together. And after we do pre-lab 7 together, you should be able to do the post 7 and 8 after that. All right, any questions on kind of where we're at and everything? So I apologize, I'm not caught up on grading. I know I have like little bits and pieces to fix. I've just been completely slammed. So, all right, let's dive into chemical kinetics now. And so now kinetics has to, of course, deal with how fast a reaction is going. So the speed of our reaction, so our reaction rate. And so it's a measure of how fast either the reaction makes products or uses reactants. And so this kind of depends what you can monitor. And it's kind of nice that, y'all went, or at least some of you were able to go on the SOU trip. So that's already kind of giving you a small idea of other ways to monitor, right? So they had NMR there, so that could be a technique. We have done, right, spectroscopy. And so we'll revisit this spectroscopy actually, right, with our UV absorbance and all that. So we'll revisit this in lab, but this is like a very powerful technique. Again, obviously your compounds have to be colored. We could also do, right, mass spec potentially. You would have to sample. But just kind of thinking about that, right? So it has to be something you can measure, some product you can track. Again, right, depending on the scenario, you'll be tracking either a product, reactant, maybe both if you're lucky, but usually you'll be lucky to track one. And then it's nice to have some ability to control the speed. This is kind of more relevant, I think, if we were to go into chemical engineering. So that kind of what separates, I would say, chemistry versus engineering is then you're actually trying to, right, optimize a reaction and get the most product efficiency rate out. And so being able to kind of control that obviously is important. And I'll put, of course, our Haber-Bosch reaction to remind us, again, what you might be doing in industry or any sort of reaction that you're trying to optimize, right? And again, this reaction takes place at extreme temperatures, extreme pressures. Again, all with kind of the thought of how do you optimize your product, how do you control that rate of the reaction too. And so we'll kind of get into some of these factors, of course, and we've seen just a general sense of this. And so generally, what we notice, and maybe you've seen this like in our other experiments in the past, is so the greater the concentration of reactant molecules, the faster the reaction. And so you can think about, well, how does a 3 molar acid solution react versus a 1 molar solution? And of course, right, think about what that means on the molecular level. So obviously greater concentration means increased frequency of those collisions. And then, right, more collisions means more probability of productive collisions, and then also, right, our concentration of gases. So we've kind of been looking at that chapter. So obviously higher pressure, higher concentration, and like we saw with our gases, right, more collisions. And then again, those productive collisions to lead to chemical reactions. And so then I think we'll actually get into quantifying this a little later in this chapter. And if I'm not mistaken, with your lab today. And so this is just a very broad statement. So it just says, again, very roughly, for every 10 degrees rise in temperature, the speed of the reaction doubles. We'll actually quantify this. So there's an equation that we'll look at so we can, again, quantify the reaction rate as it scales with temperature. And so this is the tease of it, that there's this Arrhenius relationship, so we'll explore that later in the chapter. And so something that we'll kind of at least somewhat talk about, I don't think we'll get too into it, but at least things to think about are, well, what are our reactants? So this also affects the reaction. And so let's see what it means by the nature of the reactions. And so this could refer to, either just the size, so small molecules, so just generally what we think of, right, from N2 to caffeine to drugs. So all those would be kind of more small molecule classification versus so large molecules, and you start getting into, right, polymers and any sort of more complex structures, proteins, amino acids, right, those start behaving differently since you have much larger tertiary structures. And then more for the chemistry relevance back over here. So gases tend to react faster than liquids, which tend to react faster than solids. So again, something to think about with reagent optimization, right? Is your reagent a big piece of solid? Is it a gas that you have to bubble through? You know, is it a liquid? And we've mentioned when your substance is a liquid, you can do what's called a neat reaction. So liquid substance. And so neat just means no solvent. So that just obviously helps to make a super concentrated reaction. Obviously, you can't always do a neat reaction, but just something to think about. Powdered solids are more reactive than blocks. So this would be like zinc powder. So zinc powder is technically flammable. I've actually never seen it light up, but versus like a big piece of zinc metal, like that would never light up. And so obviously, right, that's due to more surface area for contact with the reactants. And then obviously, right, there can also be periodic trends that we've looked at before. So obviously, right, some of those being the alkali metals for sure. Obviously, those have safety considerations, right, when you're trying to react them. And then even more so, right, as you go down to rubidium and cesium. You could also bring into radioactivity, right? So that's also confounding factors. So like francium is radioactive, or really any other radioactive element, right? There would be huge safety considerations. I don't think they tend to react any faster, but it's just a safety thing. It's like a big safety deal to work with any sort of radioactive elements. It like has to be in a separate room and a thing, and you got Well, yeah, a bunch of shields, and you got to have the, your exposure thing on you, so it always turns into a huge thing. And then ions tend to react faster than molecules. So again, right, we usually work with ions, right? So literally everything we work with in this class, essentially. And so then, let's just look at our few definitions. So, right, we have our rate. And so again, we'll be looking at our rate of our chemical reaction. So it's just defined as how much a quantity changes in a period of time. And so obviously you might be familiar with the speed rate. So, right, if we're trying to figure out our miles per hour of a car, so obviously the distance your car travels in a given time period would give us our miles per hour. So similarly, right, we can look at some molarity. And so we'll look at this. And so again, right, this is something that we're going to do. So then we have our rate here. So our rate of our chemical reactions is measured in terms of how much the concentration of a reactant decreases. Or again, right, we could also measure the product concentration increases in a given period of time. And so we'll look at a little graph here. And so we're looking at this reaction. So let's look at our graph. And so we have H2 and reacting with iodine to give us HI here. And if you notice, right, we're monitoring the concentration by this graph of H2 and HI. And that is probably something reasonable, right? Again, thinking about NMR, you have these little H's, so you could see them by NMR, but then, right, iodine, you would not be able to see unless you had a special iodine NMR. But that being said, I don't know that iodine has NMR active nuclei. All right, so then that's what we're looking at here. Let's see, they don't have I2 listed. But we would measure our rate. So again, if we were measuring our iodine product, how much it decreased over time. Obviously, right, you can measure 2 points on a graph. That's what all it's saying here, right? So, so our change in H2. So that would just be, right, change in Y over change in X. So let's put that, right, Y over X. So just like any other line equation you've seen before. And so again, right, that's what has been done at these 2 points. And so as time goes on, the rate generally slows down since our concentration of reactants decreases. So again, we can quantify that. And then, right, at some time, the reaction stops. And so either because our reactants run out or if we have reached equilibrium, which we'll get to what equilibrium is. All right, so everybody still with me so far? And so then, right, this is again kind of more basic calculus stuff, so we're not going to do any calculus in here. But again, right, you can just appreciate that we have our average rate, and obviously that would be over an entire time period. And so obviously the larger the time interval, the more the average rate deviates from the instantaneous rate. And then the instantaneous rate obviously is going to be your slope at any one point of our curve. And of course, right, you could take the first derivative of that function. Again, we're not going to be doing that in this class. We'll just appreciate all the work of these derivatives, right? But again, you can just kind of connect that to your calculus. And so that's all that's shown right here and here, again, at these 2 points, just measuring, right, our change in concentration over a set time period. Same thing with here. And then again, right, obviously this is another form of that same data. And again, right, are you taking the average rate, where we're looking at our entire time period of 100 seconds and how much our molarity changed, or are we looking at the instantaneous rate there? And then you can just kind of appreciate, again, how the rate is decreasing, again, which makes sense. And we'll see again as we dive into the math. All right. And so let's look back at the graph still and understand this reaction rate thing. And so again, we're still focused on this reaction. And okay, so now it tells us, and we probably know this, right? So in most reactions, the coefficient of our balanced equation are not the same. And so that means, now let's think about what that's saying. So okay, so for every 1 mole of hydrogen used and every 1 mole of iodine, we'll be making 2 moles of HI. So therefore, right, our rate will be different. And of course, we can make them all consistent though, and account for this difference by multiplying it by 1 over the coefficient there. And so now we can look at that. So right, this is, again, just the math of it. And then let's compare. And so now that's what's being shown down here. Okay, so they're showing us 2 points. And so let's look at H2 first. And we're calculating, right, our instantaneous rate. So again, right, what was shown above. So change in y over change in x. So we have, right, our rate here. We can plug it into the calculator just so we get the same number. So again, right, that's all they did here. So negative 0.28 molar divided by 40 for our time period that we were looking at. Okay, so now we get this rate. And again, it's negative, right, because it's being consumed. And then let's compare that with HI. So again, they did it for us. Okay, our change in Y is 0.56. And then divided by 40. And so, right, we haven't made the correction yet, so I'm just showing you, okay, it's twice as much, right? And that's what we expect. Since again, right, we said, well, it's forming 2 equivalents of HI. So, okay, that makes sense. And so again, now we can get our rate and account for that factor by multiplying it 1 over the coefficient. And so multiply times 1 over 2. And then, right, we get our same rate. So now the rates match. And again, right, follows this formula where the HI is positive since we're increasing it. And then, right, H2 is negative. So just don't forget to account for your coefficient. Does that make sense for this? Oh, sorry. So remember from our balanced equation, so right, there's a 2 there, so then we know it's increasing twice as much. And then to get it right to the same factor, you do 1 over your coefficient, so 1 over 2 brings us to that same rate. And then, so for better or for worse for this chapter, you have to be given data essentially. So that's like the other point of this chapter is we have to measure it, right? We have to experimentally determine it. We can't just guess, right? So we have to be able to measure it. And then like I mentioned, we have to be able to measure the concentration of at least one of our components at many points in time. And so maybe it sounds simple, but right, if you're the chemist trying to plan your experiment, this is not always trivial, right? So sometimes it involves like freezing your sample, taking it down in the machine, and then warming it up to try to measure it, right? It depends how fast your reaction goes. There's so many different kind of factors with it. And right, so it kind of mentions, again, these broad approaches. So if you have a fast reaction, so something that's complete in less than an hour, or, basically whatever you can sit comfortably at the computer for, or, right, you can reasonably program your computer to go, then you can use continuous monitoring. But again, right, you have to figure out how you're going to do that. We saw NMR, we saw the spectroscopy, mass spec potentially. The problem with mass spec is you can't really do continuous monitoring. You have to take aliquots. And so it mentions that down here. So for samples that can happen over a very long period of time, so this could potentially be, right, days, then you might have to sample it at various times. And again, it also, like I said, it really depends on the technique too. So mass spec is usually one of those where you have to take out a sample. Maybe you have to even what's called work it up and then see what it comes out to. Even if you have a very long reaction, as long as you could do it like in an NMR tube, you could keep it in that NMR tube for a week. Honestly, I've seen that before. Again, it really just depends on how are you looking at this reaction. And so then, right, your book kind of mentions just other possible monitoring systems. So, right, you could measure pressure with a gas mixture, but again, you'd have to have a pretty specialized setup for this. Polarimetry, so this is where you measure basically chirality, so like an R versus S conformation. So let's look up some example. I'm not actually sure where it'd be too helpful. Again, right, it's very scenario specific. So this is one example. So limonene is often distilled in like organic chemistry since you can extract it from citrus peels. And the citrus peel one is the R isomer. And then the negative isomer is the terpene one. So kind of more piney smelling. But that would be, one use of the polarimeter if you were watching a reaction go from one isomer to the next. But again, right, you have to have a chiral center that's pretty specific. The spectrophotometry, like I mentioned, right, we'll use this one. So this is a nice one. The only trouble with the spectrophotometry is obviously if it's colorless or if it's air sensitive, then you have to have like a special apparatus or like move it in the glove box, and that's always complications. And then, we also didn't mention IR, but it's not used as much, but there'd be like an IR or like Raman spectroscopy. But these measure like stretching frequencies. So again, you have to have like a distinct band to measure. So that's always the issue. And so, right, we mentioned sometimes you have to take aliquots out. And you saw a GC at SOU. So again, right, you can see how that analysis would occur. So, right, you take your aliquot, check it. There's a nice long column. that it runs through, right, separating it. Just a sample. Yeah, so it just means like you take a small sampling from your reaction mixture and work it up. And so, right, again, all this is to say the experiment law must be determined experimentally. And so for all these problems, right, I have to give you dummy data basically. And so our rate law obviously shows how our rate of reaction depends on our concentration. And so changing our initial concentration will affect our rate of the reaction. And so now we're just kind of given our general rate law here. And so right now we're just saying, okay, we can have some rate. There's our concentration of A, and right, it's proportional to some power. And so that's what we're trying to determine. And we'll again go over it, but we're basically trying to determine if it's zero order, so it doesn't matter, first order, whether it's a linear relationship, or second order, where it's exponential. And again, right, so now this is just kind of laying out the theory. So let's say you had two reactants, right? This is theoretically, then you'll have your rate that's dependent on reactant 1 times reactant 2. And again, right, you have to determine the orders. So again, mainly looking at 0, first, or second for our purposes. And then we have our associated rate constant. So again, this is just our basic outline of what we're going to be doing. And so now this is just kind of showing us how to read this conclusion here from what this is showing us. And so we're given our reaction. So we're looking at this. So we have 2 equivalents of NO plus 1 equivalent of oxygen to give us 2 equivalents of nitrogen dioxide here. And then, right, we're just given the rate. So again, right, you have to be given this. You can't just magically know it. And it's telling us from here, so let's zoom in. So our rate is equal to some rate law, so we'll have to determine that. And then it tells us that it's second order with NO and first to O2, right? And obviously there's just a little implied 1 there. And then you could add these 2 superscripts up, and then we can say that the reaction is third order overall. And so does that make sense, just what this expression is saying?
Is the order just defined by the
So it's actually not, so it's determined by the data. So that's what's kind of confusing about this example, is like even though it follows along, that's not always the case. So yeah, let's re-emphasize that. So must be given data to determine. Unless, right, again, like they're telling you. So, right, they're just telling us, hey, it's second order, it's first order. But we don't really know that at this point, if that makes sense. And so then, and it'll make more sense as we go through kind of examples too. And so then what we see, again, just kind of defining what the different orders are. So we have our 0 order, and our rate is equal to K times our concentration of A to the N, right? So this is just our generic rate. So then if it's 0, then it has no effect on our reaction rate. So now our reaction rate, if we plug in 0, right, is just equal to K. So it's just dependent on whatever our rate is, right? But it's not affected by A. And again, we'll do some practice problems. But again, all we're saying is, right, the reaction is going to occur, but it does not depend on the concentration of A, right, with how fast or slow it's going to go. And then make sure you grab the cheat sheet because it has everything kind of all condensed. But then your rate, so this rate will be given in molarity per second there. And then so that means your K will be given in the same units as well, right, since A has no effect on it. And so then, with the first order, the relationship that we'll see is, like we mentioned, it'll be directly proportional. So then if we were to double A, and we will double the rate of the reaction. So then our rate law will be A to the 1, or of course, just simplify K times A. And so then this is where the units come into play and get a little funky. So, right, rate is still going to be in concentration per second, right? So that's what we're always measuring with our rate, our change in molarity over time. And then since concentration does matter, right? So A is in molarity, and that means your rate is just given now in seconds, inverse seconds.
Is the order of the rate law analogous to the order of like the differential equation?
Yeah, so that's, and I think we'll see that relationship in the, like in the equations. They have that relationship. They should just be derivatives. But yeah, but again, for our purposes, right, we just care about like the happy equations. But yeah, you can appreciate the calculus behind it, which is good. And then second order. So again, right, our generic rate. So we put a 2 here now for N. So obviously if we were to double A, now we'll could quadruple the rate of our reaction. And so then now we have units. So right, if this is going to be M squared, then notice your K to get back to our rate, right? So that means K is given an inverse meter second, right? So that it cancels out to give you that again. So just watch those units. So that's why I like the cheat sheet to help you.
So could you call the first order linear and the second order quadratic?
Yeah. Yeah, because we'll see that with the slopes there. Yeah. And so, right, this is basically what we're going to be doing then, right, for our data, whatever problems we're looking at. And so, right, we'll have to figure out the rate law with multiple reactants. And so, right, we'll have to kind of change the concentration of one at a time. So, right, we'll change one, and then we'll change the other, and kind of compare those results, and then you can figure out the order. And so again, right, you have to examine something. So we're going to be examining data and figuring out the relationships. All right, so let's start with this one here. Oops. So we have NO2 plus CO gives us NO plus carbon dioxide. And so we're given here, right, our initial rates and also concentrations of our reactants. And so just kind of compare them for a second and just see if you can determine the rate law. So that's really the first thing that you want to focus on. If you're feeling, really confident, you can go ahead and try to solve for K, but just kind of compare the data, right? What do you notice? Can you figure out the orders of our reactions? So any thoughts on this one, or what are we noticing?
No, I noticed that the carbon dioxide levels through the initial work was like 4.
So that's a good observation, right? And so you were probably looking at these first 2 points, right? And you're noticing how the CO doesn't change, so that's good, because we can't be trying to figure out 2 variables. But yeah, okay, so you told us this doubles, and then this rate, what did you say again?
It doubles as NO2 doubles.
Does the rate double? Check the rate though, because is that times 2 or times?
Well, it goes up by a square.
Yeah, so
I guess.
yeah, so by 4 then.
Yeah, it's between the point 2 and point 4, and 4 and 4 goes up like 4.
So between 3 and 4 here.
Go from 0.0 away to point.
So that looks good. And then let's slow down a second though, right? Because we want to compare. This is decreasing, so that's a little confounding. But if we compare it, let's compare, trying to find where this doubles and the NO2 doesn't change. So yeah, if we look at this rate though, 2 and 3, right? NO2 is at 20. We double our CO, but what happens to our rate? Yeah, it doesn't really change, right? So that's telling us that our CO is probably 0 order. And then kind of again, right, going back to those other thoughts of our NO2 being 2nd order. Well, okay, right, this doubled again. This decreased, but yeah, like he was saying, this is times 4 again, which matches with our 2nd order for NO2, and then it looks like, right, 0 order for CO. So did everybody understand kind of how to analyze that, right? Because you'll be doing this in lab too, and well, everywhere really. So again, right, you look at where they're the same, hold one constant, double one, right? Maybe double it again, see if that's consistent. And then hold the other one constant, right? Double the other one, see how your reaction rate changes. All right, so that's good. And so now we can write our rate law now. So now we're just saying, right, whatever our rate is equal to K. And now we can say NO2 to the 2nd, right? We could write CO to the 0, but I'll just rewrite it now. K to the 2nd here. And so then the second part of our question asks us to determine the rate constant for the reaction. And so now we need to just pick any data point. I'll probably do the first one, just because it looks easy. Easy numbers. So now part B. So again, plug in any data point. And so, right, we're given our rate here. So 0.0021 molarity per second is equal to, so we're trying to figure out what our K is, times, and I'm going to plug in, again, right, one of our values. So in this case, our NO2 concentration is 0.1. And so now we can just solve. Oops, sorry. And so then I get K is equal to, and so right, don't forget your units. So you could either look at your cheat sheet there, or I'm just trying to think of my units, right? I'm trying to get back to molarity over second. I'm trying to figure out my units for K, right? I have molarity squared from my rate law, so then this has to be 0.21 inverse molarity inverse seconds for those units.
So if that was the case, though, then wouldn't the last one be
Sorry, where?
on experiment number 2, it goes to 0.082. And so the factor goes up by a factor of 4 when it's going to increase molarity.
Yeah, so we could plug that in, right? So let's see what you're saying. So what we should be able to do is right now we have our K, so then we can take 0.2 squared, right, times this K here. And so that does give us about what the data had said. So yeah, that matches. Any other questions on this type of problem? So this is a pretty standard problem for this chapter, right? So you'll have to do this probably on a quiz, on an exam, right? Looking at your reaction rates. All right, so then this is just now, right, our integrated rate laws to try to get us to more equations on there. And so like y'all are recognizing, so we can apply calculus to integrate our rate law, and it gives us our other equation, right? And so now this is our integrated rate law. And again, all you need to take away is the two formulas, really. And you could appreciate this, right? You have your cheat sheet to guide you. And so we have, right, our rate law, and then we take the integral of it and get back to here, right? So now we're just saying that the concentration of A at any point in time is equal to negative KT plus whatever our initial concentration is at. So that's for our zero order. And so again, right, your problems that we're going to be looking at, you're mainly figuring out, do I use this equation or do I use this equation, right? Just depending on what the problem is set up as. And then you can appreciate the graph, of course. So again, our zero order graph, time versus concentration, is just a linear slope equal to negative K. And our y-intercept, of course, would be our initial conditions. And so looking at first order, so again, right, we had our rate law, and then now our integrated rate law gives us our natural log then at any point that we're looking at is equal to negative KT plus the natural log of A at our starting point, again, initial conditions. And so now it's the natural log of A graph that gives us a slope. And again, our y-intercept is the natural log of A. And then when we look at half-life problems, like when we're talking about radioactivity, this is usually the half-life equation that we want to work with. And so this is just simplified already to be at half the point. And so just telling us that, and this is, again, right, already simplified. So 0.693 over K is what that simplifies to for a half-life problem. And then second order, so now we have 1 over A at any point in time is equal to, notice that's positive KT plus 1 over our initial starting conditions. And so now our intercept is 1 over our starting conditions, slope is positive K, And then again, right, we're graphing 1 over A. And so then, right, I printed this out for y'all. Since this is basically, right, all you need to know for this chapter, essentially. So, right, you have your rate laws, units of K to help remind you, the integrated rate law, which again just helps us with certain types of problems, and then our half-life expression. So obviously, right, you have other half-life expressions for the different orders, and then I just tell you to start this one. So this is more for our radioactive problems. So most of the radioactive decay problems are all first order. All right, that's probably a good point for a break here. So yeah, let's take a little break and then we'll keep looking at half-life and a little bit of radioactivity.
Why is this, says -7 on all of these except for the last one? Just want to understand why.
I mean, I don't have a map on there right now. Because it's just that if you were to do the integration, it's supposed to calculus. So as we come back from break, I just wanted to share this CNN article that's talking about, well, you can look at it. So right now people are trying to discover elements, right, 119 and 120. And so I can post a link to this article, but you can, right, first picture where those elements have to go. And right now, some people kind of say that the periodic table, obviously the one in the back room is now outdated, but you know, it looks nice and complete to 118 over here, all nice and filled in, right? But kind of the emphasis is there's more elements kind of theoretically And so, right, people are trying to discover this. And so they're just bringing up that Japan is trying to win the race here. It goes into some of the politics. So obviously there's issues with the Russia collaborations right now. So unfortunately those scientific efforts aren't going maybe as fast as they should be. But yeah, they're just talking about also how they're trying to collide them. So obviously this is also different than what we're about to talk about, right? So this is fusion, where you're trying to take lighter elements and make heavier ones. And so they go into some of the things that they're trying. So apparently the Riken researchers, so that's the Japanese team, they've been trying to bombard vanadium and curium together. And that equals, of course, 119 protons in theory. And so they're trying to figure that out. And then, of course, again, all these things are very short-lived. And so this is just showing their possible combinations that they were working for, why they settled on the vanadium one. And I don't know if we've talked about this specifically in this class, but kind of this is the idea, this whole island of stability. So again, kind of what we've talked about, right, with filling the shells, but then what if you keep going in theory, right, and going to those higher order theory shells, and so kind of trying to figure out, right, stable elements. And it mentions, right, that even if they do make them, they'll only last for a few milliseconds, so trying to detect it obviously is difficult. And here's a good application. So technetium, so this was one of those elements. So we'll see this in some of our examples, and you often see it shown like this with this little M, and then M always means metastable, so it's going to decay. But yeah, so apparently it can be used to detect bone cancer, which is kind of interesting. Well, that's kind of the hope too, right, with these new synthetic elements, that maybe they'll have a half-life that is, even though, right, it'll be short, maybe it'll be useful to do something. Maybe I can post a link to that if people are interested. Okay, I'll post that. And so now, going back, so again, now this is fission. So now they're splitting apart, so different idea. And so this is, right, half-life now for, again, when we talk about radioactive decay for the most part, such as with carbon-14. And so the simplification for half-life here is, of course, it's the length of time it takes for the concentration to fall to half of its value. And we have our first order reaction. And so you sometimes see these simplified problems where, right, it asks you, well, at one half-life, how much of the parent material do you have? And you can set up these charts, so half-lives, percent of parent. So right at 0 half-lives, obviously you have 100% of the parent is what it's called. And then 1 half-life, right, 50% is gone. Now you have 50% of the parent, right, 50% what's called the daughter nuclei, so whatever it decays to. So that gets into, right, decay chains. And then obviously, right, this can just keep going. So 25, 12.5, so etc. Or you could always, right, solve this mathematically, so plugging in using either this equation or probably finding, right, this equation more helpful as well, trying to figure out, right, if you've given, you know, your initial conditions, how much is left over, you can figure out, right, how much time has passed by. So then radioactivity. So just looking a little bit at radioactivity in this chapter. So obviously that's just defined as the release of high energy particles and or high energy electromagnetic radiation from the nucleus of the atom. And so, right, anything that ejects particles or energy is referred to as being radioactive. And so radioactive nuclei spontaneously decompose into smaller nuclei, so that's just known as radioactive decay. And obviously, right, radioactive nuclei are unstable. And so like we mentioned, right, the parent nucleide is the one that is undergoing the decay, and then the daughter is whatever the product is. And so anything with 84 or more protons is radioactive. And so then we'll go over kind of the main types of radiation or radioactive decay. And we'll look at these other ones as well. All right, so we'll start with alpha decay. And also, so again, right, if you ever get bored, you can look at these chart of the nucleides, right? And this tells you all the atoms and all their decay pathways. And so you could see if we can zoom in on this, of course. I was trying to find one that was an alpha. Just like these yellow ones. And so, right, it mentions that this platinum one undergoes alpha decay. So again, right, you can just see all the possibilities. And so what does that mean when it undergoes alpha decay? So it just loses this nucleus. So, right, a helium atom. So 4 for our mass, 2, of course, for our protons. This is more of the classic example of the alpha decay. And so this would be uranium-238. And then notice how the math adds up, right? So everything is conserved, so your mass is conserved. And so if you lose 4 for your alpha, so 238 minus 4 gives us 234 for thorium there. And then, right, you lose 2 protons, so same thing. You go from 92 to 90 for uranium to thorium. And so alpha decay is the most ionizing but least penetrating. So, right, you can protect yourself with clothing or paper, right, cloth. And again, right, when you lose your alpha particle, the atomic number decreases by 2, and our mass number decreases by 4 there. So again, you can see how that adds up. And then, so let's look at beta decay. And so there's really 2 types of beta decay. And so this is what I call negative beta decay. And you might see it referred to such, again, depending on what resource you're looking at. And so this beta decay or negative beta decay, as I'm going to refer to this more specifically as, it's when we have a neutron that essentially breaks up, right? So it releases a proton and then also, right, our beta particle. And so it emits an electron-like particle. So notice, right, it's massless. And then formally -1 on, right, the number there so that our math adds up. So again, right, you're kind of seeing that these 2 particles put together make a neutron. So that's where it came from. And then beta particle is 10 times more penetrating than an alpha, but only half the ionizing ability. So again, right, you can be protected with heavy cloth. And then let's look down. So I didn't put my example there. So here's, let's zoom in on that. Here's the classic example of this negative beta decay. So this radon 228 going to 228 actinum. And so again, right, it's going to eject this little negative particle, so massless. Notice, right, so your proton number formally goes up as that neutron, right, becomes a proton and ejects that electron, essentially. But again, the math should add up nicely there. And so here's another example of beta decay shown here. So, right, we can have our carbon nucleus going to our nitrogen 14. So again, right, our neutron becomes a proton, our beta particle is emitted, and then that's why our number formally increases there.
Would you call that positive beta decay?
So this is still negative beta decay, right? So it's still negative. But yeah, let's look at positive. So we'll skip gamma for a second. And so your book refers to it as positron emission, but other sources will call it positive beta decay. And so again, now that's kind of the opposite, right? So instead of now shooting off this little electron-like particle, it shoots off this anti-electron, as it calls it, our positron. So still massless, right? But now it just has a +1 for its number of protons. So, right, it's essentially a massless proton. And again, right, we see our proton, in this case, now transmutes to a neutron. So notice, right, the mass stays the same in these chemical reactions with our positron. Electron, or positron is lost. And then, of course, right, protons do go down now in this case. And so again, right, this is our classic example of a positron, or positive beta decay. So again, phosphorus 30 going to silicon 30, and again, right, the math all adds up there. So then going back to gamma. So gamma, you might have to be told that it's a gamma is usually how these are. So there's no loss of particles from the nucleus. So it just goes from like a higher energy state to a lower energy, such as that technetium example. Let's see. Oh. Just trying to find gamma on here. And so, like I had mentioned, you might see that little M on something, and that lets you know, right, that it's some sort of metastable, and it might decay, especially, again, by the gamma route. And so, again, right, gamma is massless and chargeless, so, right, it has, this is just our symbol here. And then least ionizing, but have the most penetration. And so, right, you would have to use like a lead plate, or sometimes, right, they're called like lead pigs or something, where you have like an enclosed case, right, to put your radioactive elements in there. And so, right, it's usually coupled with some sort of other arrangement. So it could like I said, either undergo spontaneously, like in the case of that element, or you'll see it coupled with one of these other processes, sorry. And so, right, you might see it paired with other types of decay. So then we went over our positron emission. And then the last one, which is kind of, this is a little oddity, in my opinion. And so we have electron capture. And so it's kind of in the name how it's different. So, right, so instead of splitting, it's first captured, right? So it's pulled into the nucleus. And so it happens when a proton and an electron formally combine, and then they make a neutron. And so that means our mass number stays the same, but then, right, our atomic number decreases since our proton became a neutron. That's what it's listed as, but yeah, like I'm saying, it's a little bit different, right? Because it has to capture the electron first, so you have to do some sort of like electron bombardment, maybe, if you wanted this to happen.
What's that called? That process?
I mean, it's still just considered, yeah, a radioactive decay, but it's just where you have the electron gets captured first, right? So then proton plus electron, neutron, and then sometimes, right, that could also lead to further decay. And so here's, again, the classic example of that. So you have 92 ruthenium. Again, right, notice how the math works out. So 92 is conserved, and then since we're capturing the electron, right, our protons decrease. And so, like we're seeing, all our nuclear processes are described with these nuclear equations. And so again, I think it's kind of nice, since like we were seeing, the atomic number and mass numbers are conserved, right? So it's kind of easy then to figure out what the unknown products are. And so obviously the sum of the atomic numbers must be equal, along with the sum of the mass numbers on each side. And so again, right, it's easy to tell from a problem. So, right, you could be given, you have your parent 238 uranium isotope. It undergoes alpha decay. What's the product? And then, right, obviously it's easy to subtract 4 and 2 to get our 234 thorium there. And then obviously, right, once you get the 90, you can go look at the periodic table to see what element matches. Questions on that? Okay, I think we might do the, would you rather do the acid-base titration math now, or would you rather just work sample problems from this chapter right now? Thoughts, opinions? Okay, let's do our sample problem then. All right, so just start off with this one then. So what's our half-life for the decomposition of NO chloride here when the concentration of NOCl is 0.15 molarity, and the rate constant for the second order reaction is 8.0 times 10 to the negative 8 liters per moles per second. So how's this problem looking? Hopefully the cheat sheet should be helping.
I use the backup expression on the right side, and put the 3 nanoseconds.
Oh, wait, slow down. So let's, I just want to look at the formula, if I can find it. So you said you picked,
So I chose the second order here.
so second order, so this equation?
Yeah, I was putting to use the now 15 minutes, volts, 10 seconds. So,
Sweet, so that looks good. So so again, right, make it simple on yourself. Kind of pull out all the pieces, right? It told us it was second order. It was asking us for half-life. So yeah, you can just pull out this equation, right? We're given the initial concentration there, so that looks pretty nice for this. So I'm just going to rewrite that for a second. So again, right, for our second order, T half-life is 1 over K times our initial concentration. And so then, I assume you just plugged in from there, correct?
yeah, I got 23 minutes, 10 milliseconds.
I'm just not sure I got that answer. So 0.15 times 8 times 10 to the negative 8. So I get that answer.
That's because I didn't use parentheses.
Oh, okay. That's, so yeah, make sure, right, always good to work the problems in class. You don't do calculator errors. So what is that? 1, 2, 3, 4, 5, 6, 7. So 8.3 times 10 to the 7th seconds there for a half-life. And seconds just because, right, that's consistent there. Questions on this one? All right, let's try another one. So we have a half-life of a reaction of compound A to give us D and E is 8.5 minutes if the initial concentration of A is 0.15 molarity. So how long will it take for the concentration to drop to 0.03 molarity? And then it asks us if it's first order to A versus second order to A. let's see how your first order is going. And so what do we maybe have to solve first? Just kind of looking, I'm trying to pull up the cheat sheet. So we're looking at our first order equation.
We weren't given K, and we need to get a solve the equation. We were given a half-life, so we can use the equipment to find
I like it, so that's good. So yeah, exactly, right? So let's do that. So we'll solve for half-life first. So ln of 2 over k, or right, the 0.693 over k is equal to, so they told us the half-life, 8.5, so minutes. So then now if we solve for k, bless you. And so now I get a k of 0.0815. So that's going to be minutes. Bless you. Double check, right, our k. So yes, per minute though, right? So it says per second, but just pay attention to the units, right? So obviously these were given in minutes. And so now that we have this, we can plug it into this equation now, right? So then it was asking us, how long will it take for the concentration to drop? So that's, right, a good indication that we want to figure out some initial concentration and then some other point, yeah.
We can also multiply the half-life by the square root of 5, and we do the same number. So, multiply by 2, it's 2 half-lives, which is 4, and 2 to the square root of 4. So multiply by the square root of 5 and get an absolute value of G for this. So it's 1/5 of what the value was when we started with.
Yeah. All right, so let's, yeah, that's different tricks. So let's plug it in though. So I'll just plug it in with the numbers. And so then, oops. So natural log, again, going back to our formula, right, at a certain point in time. So 0.03 over 0.15 is equal to negative 0.0815 times t. And so now, what do we get for t? So I got 19.7, and then that would be minutes for t. So did we get a chance to do part B yet? So yeah, take another minute or so, right? Repeat that now for B. So second order, so you might have to do the same thing, right? Solving for K first before you can plug it in. So how's this one coming along? So we can just kind of repeat the process, right? So we have second order this time. So prior to calculator T half-life again. So this time 1 over K times our 1 over initial conditions. So in part B, so again, right, solve for T half-life, so 1 over K times 1 over our initial conditions. So then 8.5 minutes is equal to 1 over K, which we're trying to solve, times 1 over 0.150. No, did I do something wrong? Oh, I should be dividing. Sorry. No, that's also wrong.
Should be 1 over.
There we go. Oh, right, to get to K. I was being dumb there. Yep, okay, so then to solve for K, so then K is 0.784, and then, right, that's per molarity per minutes. The only odd thing is our time is a little off. And then from there, so we have our K now. So now we can use this formula to get the second half of that problem. So again, right now answering how long will it take to drop to 0.03 molarity with our new K. And so now I'm just copying the formula. So from our cheat sheet chart, now just finish plugging everything in. So 0.03 is equal to 0.784. Let's make sure we're in minutes. Trying to solve for T. And so then, do we get 34 minutes for our second T? I see some yes.
What exactly does ASIN represent?
That's just the value at the certain T point. Yeah, right, so if it's A at T, right, so then the problem was asking us to find what the T was, so how long it takes to get to that concentration.
So is that like 30?
Well, it's a variable, yeah, but it's saying, right, what your concentration of A is at any point in time, right? Because T is anything just as long as it's not the initial condition.
Just take the inverse of that and
Well, once we solve it, right, so we put 1 over that, and then, yeah, doing the algebra, right, minus the initial conditions divided by K, so yeah, and then we got T. So that's just telling us, right, how long it took to get to there. questions about those two? All right, let's try, we'll do one more for today. So the skeleton of Richard III was found under a parking lot in England. And so the tissue samples collected from the skeleton contain 93.79% of the carbon-14 expected in living tissue. When did King Richard die? And it gives you the half-life for carbon. I think he was. It's always first order. Yeah. At least in our problems when we. So yeah, as you finish up the problem, so you can look up the Wikipedia, or probably want to find a better historical reference in Wikipedia, but yeah, essentially King Richard's body, or King Richard III, his body was lost. He was killed in battle, and then basically they lost it and didn't know where his body was buried. And so, yeah, it was found, or at least there was some like Greyfriars compound where his body may have been buried. And so then they were playing around and trying to find some bodies, which they did. And this was pretty recent, actually. So this was 2012 when they were doing that work. So they found some bodies. And then, of course, right, what's kind of cool is obviously, right, they had to do a different sort of analysis. So obviously our problem is a little simplified problem of what's going on, but it mentions, right, that they try to do DNA analysis as well to figure out which one of those skeletons was actually King Richard. And then it does mention the radioactive decay and carbon dating. Not to get too into the rabbit hole, but it does also mention kind of the difficulties of radiocarbon dating, and even so it mentions that there could be too much like seafood consumption, and so that gets into, right, the ratios, because it's all about like the present material, carbon-14, right, that's integrated in your body. But if you have something where maybe you have just an effect where you would have more radioactive isotopes for some reason, and that can be confounding. But yeah, they said that it was at least consistent with the date, so that's kind of interesting. But yeah, it looks like they had to go through mitochondrial DNA and then, of course, other tests. So again, you can obviously see, right, the extensive testing that's needed. All right, so what do we find with our little sample problem here? So again, roughly what you would be doing. And like I had mentioned, so treat most half-life problems as first order when we're talking about radioactive decay. Oh man. Running out of time. So then T half-life is again this equation. So we can find our K. So we need K again. Oops. It would help if I could punch it in properly. So then we're given our K, and now this is in years, so 1.2 times 10 to the negative 4 years. And so then 93%, so we can set up our other equation of part over whole. So I just took, right, this equation. Obviously, 0.0 is going to have 100% of the parent material time T, right? They told us it was only 93% of the expected carbon. So equals negative KT. Oh my gosh. KT. And so now we just need to solve for T. And so how many years did y'all get? 530. And so, right, seems reasonable. And like we were reading from the article, yeah, that's about what they determined as well from the real radioactive dating. But of course, like you saw, right, probably need more evidence. So the DNA, the dental records, if they can find any facial structure. All right, we'll end there. We'll do more practice problems. On Thursday, we'll do the titration math and just keep practicing for Thursday. So we won't have a quiz this Thursday, and then we'll just start up again with chapter 17 next week. Yeah, so we kind of skipped 16 quiz-wise, but that got covered on the exam at least. And then I'll see y'all in lab. Should be a fun lab.